Hello, arcade lovers and enthusiasts. Here I have a new repair started already. This is Atari's Missile Command. Now, this is a dirty board. It's got a lot of nastiness on it. Caked in dirt, I guess. Weird. I have already gone through and it had some broken caps. You can see there's a few broken caps in the garbage here where I've already picked those off, cleared out the holes. Crystal was broken, removed the legs and cleared the holes. Removed all the ROMs and the CPU and Pokey over here. These sockets will be replaced because, as you know by now, these are not reliable 40 years after the fact. 45 years after the fact, basically. They just do not, they're not good. So we'll replace those. Clean this thing up. This has to be cleaned. It had a burnt finger on the end here. I've repaired that. Put a piece of copper on there. Wrapped around, tinned it. I soldered it to the ground plain and I tinned it well, so that needs to be washed off too. So I'm going to take this inside right now and give it a good scrubbing. Clean this thing up. That's the first order of business. Clean it up, get it dry, and then we'll start working on it. Removing the sockets, repopulating what is broken away, and then go from there. Alright, and you can hear the air compressor in the back. I was just blowing some of the excess alcohol off of this. I scrubbed it with Simple Green with a toothbrush, loosened everything up really good. I rinsed it really good. Then I blow dried it with the air compressor, and then I sprayed it down with 91% alcohol, let it kind of displace the water, and then I sprayed that again. And this board looks new. Super clean. Looks great. So next order of business is to replace these sockets. I'm going to let it dry completely. I'll let it air dry and then we'll work on these sockets. Alright, board has been cleaned all up. I think I already showed that, but I've replaced the broken caps with these discs. Sockets have been replaced. Board has been scrubbed of flux. So we can repopulate and plug this thing in and see what it does. And I replaced the crystal, of course. 10 megahertz crystal. So yeah, we're ready to just put our chips back in it and see what it does. Okay, 6502, Pokey, 820, 821, 822, 823, 824, and 825. So we can plug this thing all up and ready to go and fire it up. Fire it up, fire it up. And it does not seem to be doing... Oh, wait, do I have it hooked up? I don't have it hooked up. Hold up. Hold up 1 second. Let me hook the monitor up properly. I've got the black and white monitor hooked up. Fire it up. Fire it up. Alright. Now I have the monitor right. Well, let's see what we get. Anything? Nothing. It's doing this nonsense. Which means it's in reset, pretty much. So we've got probably ROM or RAM failures of some sort. Could have a CPU failure. Who knows? Alright, well, first thing I'm going to do is verify that I didn't bend any legs or not some of the legs didn't make it into the sockets. I don't think that's the case, but you never know. And after that is sorted out, I'm going to try a new CPU. And then if that doesn't do it, then we'll put the Fluke on it. It's given us different colors. Alright, I did the leg check. They're all good. I put a new CPU in it. Same thing, no change. So the next thing to do is to put the Fluke on this thing, do some ROM checks, do some RAM checks, and see how that circuitry is all working or not working. E850. E850. Okay. All of the ROMs are good. So we have no ROM failures. RAM, let's do our first 1K, or is it the first 512 bytes is, I don't remember. Anyway, let's just do 0 to 1FF. That's the first 512 bytes. We got a 04 error. Read write error at address 0, bits 04. So we have 1 bit no good, and it is the 4-bit. I'm going to loop it. I'm going to grab a RAM 4116. Just grab a 4116 and jump over that bit and see if it clears up. Zero, 1, 2, 0, 1, 2, 4. 1. There it is. It's cleared up. Now let's repeat the test. And it gives us the decoding error. But that might just be the RAM. It's hard to say. Let's do a RAM short. Yeah, it's giving decoding bit 3. I'm going to go ahead and replace that RAM that I know is bad, and then we'll see what it tells us then. Okay, I replaced that RAM, and that was, remember it was saying 04. Well, this is the 1, the 2s, the 4, the 8, and then you have the 16th, or it's going to be, 1, 2, 4, 8 on the high bits, the high 4 bits, the low 4 bits. It said 04, so these 4 bits were okay. These 4 bits, the 4-bit RAM was bad. 1, 2, 4, 8. 1, 2, 4, 8. So I replaced that. Now we're not getting a data error anymore. I can repeat. This is the work RAM for the CPU, and it gives us decoding error, bit 3. So we have a RAM decoding address bit 3. Okay, so address bit 3. Let's do this. Let's get a piece of paper right here. Okay. And pencil, maybe not, maybe nothing. Here's a pen. Does it work? Yeah. All right, it does work. So let's grab this. Sorry. Okay. 16-bit address. Okay. Here's our 16-bit address, and it's telling us that bit 3, 0, 1, 2, 3. Right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So let's say we write at, and the RAM, for the working RAM is 0 to 1 FF. That's work RAM range. So if we write A into address bit 0, let's see if we read AA from address bit this 08, because remember this right here, this bit is what it's telling us we have an addressing, so I don't think this matters what it is. So if it says, if we write AA into 0, we may be able to read that same AA out of 0008. So let's try that. Let's write AA at 0000 AA. Okay. Now let's read from, first let's read from 0000. Okay. Now let's read from 0008. It says FA. Let's write AA at 8. Okay, AA. Right? Now let's hold up. Let's write 00. We're going to write 00 there. Okay. Now let's read from 0008. We get 00. Let's write at 0000 AA. Okay. Now let's read from 0008. And it's still 00. So, okay. I don't know why it's giving us a decoding. It's not 0008 is not coming out the same as 0000, which address bit 3 is our decoding issue, right? 0, 1, 2, 3. Bit 3, that's what it's telling us, right? Oh, now it's giving us a read-write error. Now it's giving us that decoding error. Yeah, it's giving us random stuff now. Bit 3. Okay, interesting. So right at read at FA. Yeah. Yeah, this is random. It's not, I don't know. We're going to have to look at it. It's not as simple as, well, it just doesn't matter what's up with this bit. It's not that simple. There's some other kind of decoding issue. This could be a problem with the driver sending data back to the CPU. So something's not right. We'll figure it out, but it's not as easy as just it being address bit 3, I don't think. There's something else that's random here. So, all right, I'm going to have to think about it for a little bit, and I'll get back with you. I got to thinking this might just be a bad RAM. Right now we are looping. I'm looping this error, and I jumped a RAM over all of these, and when I got to the very last one, it cleared up our error. So I think we just have this RAM right here, which is corrupting the addressing. So we'll go ahead and remove that guy, replace it, and I'm thinking that we should be okay. Let's try something. Let's try jumping this to where it says okay again. Right? Okay, it says okay. Let's try repeating. Now it's just giving us bit 1. That's this one. So I think we just need to replace this chip. Back together, I replaced that RAM. And I've already run the test. I will rerun the test. I don't know what the actual RAM range is. Here is the 3FF. Nope. More working RAM. More working RAM at 600 to 63F. Let's try that. I'm skeptical. 600 to 63F. Hey, good to go. Screen RAM 6F0 to 3FFF. Very strange bit of RAM. That's going to take a while. I'll be back. Alright, that region was good. It looks like we have more screen RAM at 200 to 5FF. That'll be the final test. RAM 200. And yes, this will be good, I'm sure of it. Yep. And the last test I can do is check the dip switch, how it reads dip switches. Option switch inputs. 4A00. Is there another one? Or is that other one just fake? Option switch 4A00. A00. It's got to be this one, right? Let's read 4A00. It's telling us DD. DD. Boy, that's pretty janky. This thing's pretty beat up. DD would be 1101 1101. So I believe it's 1101 1101. So let's loop this. Just loop it and start messing with the dip switches. Let's put them all this way. This should be FF. Or 00. Okay, my bad. So FF, I don't know if we can get FF with this, to be honest. These dip switches are broke. Yeah, FD. We can't get this one to F unless maybe I can, I don't know, maybe I can, there we go. FF. FF. Dip switches work. This guy works. It's just a little broke, but it'll be okay. It'll be alright. I'll check the dip switches and I'll switch them to English and all the normal type stuff. It was on DD, right? So let's do DD. Let's put it back to DD. I guess I can put the Fluke away now because its tests are all complete. We'll pop the CPU back in it and see what we get. Alright, moment of truth time. We're all hooked up. Let's see what we got. Uh-oh. No, boy. Huh. Let's put her in test. Nope. Nope. No, boy. No. Here we go. No, here it is. No, no. This time. No. Okay, just for good measure, I just got done. I put the Fluke back on it from just a sanity check. I redid all of the ROMs, good, and I did a whole 0 to 3FFF RAM check, came back good. So what I'm going to do now, and I kind of like to do this, is I'm just going to poke around on the board. I'm just going to turn the little scope on, and I'm just going to probe around until I find something that looks goofy. Instead of studying the schematic and everything, I'm just going to go through, and I usually go and I just probe outputs on chips. I don't even bother with the input side of the chips. I only probe outputs because every output is an input, right? Every input is an output. So I just go through and I check all the outputs on chips, and until I find something that's goofy. So that's what I'm going to do. That's how I'm going to approach this. Yeah, so, all right. I will report back when I find something goofy. Okay, I've been doing, like I said, just poking around on here. And I've come to this. I was actually poking around right here on these chips right here, which are the muxed addressing or whatever, you know, for the RAM, and probing the select line, and it's always selecting 0. So this thing's always selecting 0. Trying to see what I'm looking at here. Okay, it's always selecting A, I suppose, which is the buffered address. So the buffered address is always getting through. And the buffered address getting through would let me know why, you know, okay, of course, I can put the Fluke on it and I can do my RAM checks and it's okay. It works that way. Because the buffered address from the CPU side of things is always selected, it always gets through. But what's not being able to happen is the system is not being able to get through to access the RAM. And it took me back to this chip right here, which is the 163 at R4, which is the muxed address selector line. And if we look at that, it's right here. I'd like to look at the clear line. It's not clearing. Here's the clock line. It's a busy clock. Our enable lines are both 1s, which means it'll always count. We've got a load signal. Every now and again it loads, periodically when it's supposed to, apparently. But our count bits are non-existent. These are the count bits and the trickle bit. So yeah, this thing isn't doing anything, this 163 right here. So we need to replace that 163. And just to show, this is how I do a comparator. Just pull the outputs off of the chip underneath, and then you can probe what the outputs are doing on the good chip. Count bits. Yeah. And the lines underneath it are not counting, so yep, there's your problem. Okay, I've replaced this chip. Now, originally it was a 163. I put it at 161 in just because I have a ton of 161s and I don't have but one 163. And they are not the same chip. The 163 has a different reset circuit than the 161 does. But if reset is pulled high on clear, I should say, if clear is pulled high, then you can use either a 161 or a 163. And you'll see here that the clear pin is pulled high through a resistor. So we can use either a 161 or a 163 right there. If there's a signal, if there's an actual signal going to pin 1, which is the clear line, you have got to use the chip that the circuit is engineered for. So if, just for example, if you got, well, like I said, if you have a signal going in to clear this chip periodically, and it originally called for a 163, then you need to use a 163. You'll get goofiness if you don't. So anyway, let's go ahead and fire it up. There we go. Oh, it's resetting. But we're getting further. Alright, well, let's put it into test and see what we get. See if it tells us anything. Oh, it's telling us bad chip. That's the Pokey. Everything else looks okay, okay. We have to figure the dip switches out. Well, let's try putting a Pokey chip in. This Pokey's apparently no good. So we'll put a good one in there and see what we get. Okay, new Pokey. One of them. That's better. Yeah, that Pokey's no good. This one right here was no good. This is one of my new old stock Pokeys. There you go. Okay, well, we've got color issues. That could very well just be color RAM. So we'll check the color circuitry and find out why our colors are goofy. Well, it's running. That's good. Color issue. All right, yeah. I think what I'm going to do right off the bat, right off the get-go, is I'm going to desolder and remove this color RAM right here. It's a 7489. I'm going to ooh, it's burning hot. It's got a super hot spot in it. No, it's not so bad. Maybe it was just... Anyway, I'm going to desolder and remove this. I don't want to cut it out because I don't know whether this is good or bad. And RAMs are not easy to test in circuit. So I will just go ahead and desolder, remove this, put a socket in there, put a new chip in there, see what happens. If we get the exact same thing, yeah, that is pretty hot right there. That's a pretty hot spot right there. Yeah. Ooh, I'm going to say this is no good. That's really getting burning hot. I'm going to say there's something up with that chip. Okay, I've desoldered and replaced the 7489 right here. 74289. Anyway, let's give it a shot. Oops. We got to plug it in. Right? Ugh. And here we go. Will the colors be right? Yes. Oh. Well, the colors are right, but there's still that goofiness. So we have a combination of stuff. Okay. Interesting. But our colors are now at least correct. But now we've got that problem with the trailing the cursor. Well, we're one step closer. But I would say that definitely proves out that the 7489 RAM was bad. So we've just got some kind of a blanking issue or something with the cursor. We're just missing a signal to blank the behind the cursor or something like that. I don't know. We'll figure that out. It's in the it's got to be in the motion object circuitry. So get that part of the schematic out, start looking around. All right, good morning. 'Tis a new day, and I came in, turned this thing on, and it decided to do this right off the bat. No signs of life. And I was like, all right, well, let's put the Fluke back on this thing. And I'm going through ROM checks, and I cannot read this ROM. Good, 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 bad, good, good. So I just went into the address decoding and looked up that chip, which it's over here actually. It's right here, 823. So if you follow that back, it's the low line here. You turn this. It was this low line right here. And we have an AND gate that ANDs together these two signals, ROMs 6 and 7. So first thing I want to do is look at ROM signals 6 and 7, which is pin 6 and pin 7 of P2. P2 pins 6 and 7. That's right here. And as you might be able to see, I've already kind of looked into this, and I already know this chip's bad, but I'm going to show you the process of how I did it. So I checked pins 6 and 7. I have this looping on this error at that address. That's this ROM right here, and I'm looping that so that I'm constantly hammering this enable. Because if I look at this enable, pin 20, 13, 14, 15, 16, 17, 18, 19, 20, it's high all the time. And it should be low right now because I'm trying to access this ROM continuously. So pins 6 and 7 were ROM signal 6 and 7. And I'm looping this, so I should have a signal. This is pin 6. And there you can see it does go low for a portion of this. And here's pin 7. You can see there are signals on there. Then those signals come over to is that the right one? No. Yeah, those signals come over to this guy right here. The 08 at R2. Pins 4, 5 out to 6. That's this guy. Pin 4, 5 out to 6. So here's pin 4. There's our signal from that 139. And here's pin 5. And here's pin 6. Pin 6 never goes low. And if either one of those go low, 4 or 5 ever go low, pin 6 will go low. It's an AND gate. And it never goes low. So that is the issue. So this guy just decided to stick high. As soon as I came in here and turned this thing on, it was dead. It didn't even try to boot and then die. It was dead. As soon as I turned it on, it was dead doing this. So we'll have to replace this 08 and then move on. And I know I said yesterday something about option motion object circuitry. Nix that. I think this problem is going to be in the color circuitry. Something where so that's where I'm going to start. I'm going to start at the color circuitry and work my way back. And hopefully we'll be able to find this issue that way. So yeah, start with the color output, and I'm going to work my way back from the color outputs. So let's replace this guy so that we can see what's going on. All right, and after a brief pause in the action, I got that 08 replaced. Now, so let's see if it fixes it. There we go. We're back in action. We're back in action. So, yeah, let's find that issue. So I'm going to start with the color outputs and work my way back. All right, I analyzed all of the 153s with my actual analyzer, and they were all good. This one I didn't love, but it wasn't bad. Sometimes you see a chip and it just doesn't look great, but it's not going to affect the system the way that it's processing. But I just put an orange dot on that one, but that's not an issue. I'd be wasting my time if I replaced that. I got to looking over here and I was like, okay, what is this all about? We got a couple of data bits up here, right? And they come through this 125, and those are both enabled when this signal goes low out of this 00. And the inputs to that are buffered, read, not write. So you know that'll be a busy signal. And then MAD select, multiplex address select, you know that's going to be busy too. So I automatically was like, man, that thing should be doing something, because I probed on that. And when I probed on it, it is always high. This is that signal. And I've got a snapshot here, right, of that. This is that buffered read-write signal, and this is the multiplexed address signal. It's a 00, which is a NAND, so you need two ones to get a 0. We should have 0 pulses over here. So that would activate this 125 to send these data bits through. So data bits 6 and 7 could be having an issue with this. It could be something to do with this, because I believe that this problem is not in the color circuitry, it's in the video circuitry. And the video circuitry works off of the CPU getting information and loading it into RAM, and then the hardware picking that data off and moving it up and blitting it onto the monitor, right? So the CPU is constantly grabbing data, loading the RAM every vertical refresh or whatever, and every time it vertical refresh, the CPU's throwing new video data into these RAM to be picked off by the hardware, so that the CPU can go and do other stuff. And then when the CPU's doing other stuff, it's grabbing more data from random places, and it's got to be grabbing data bit 6 and 7 from this guy, but it's never being enabled. See, if I just stop it, okay, that should be, you need two ones. You need two ones to get a 0 on this line. There we go. We should have two ones here. Two zeros, I mean, on this line. And there's two zeros, it should be. So this thing's no good, this chip right here. And that's going to alter our data back to the CPU. That's going to give the CPU a new instruction every so often. Data bit 6 and 7 is going to be different. So I want to replace that, and then we'll see. That's got to clear this up, I would think, because that's going to give the CPU new data to load into the RAM. It's going to change the data that's being loaded into these RAM. So yeah, so let's do that. Okay, yeah, I jumped a 00 over this chip, and I had initially jumped it over it without pulling the leg out, and is just holding it high. But I removed the leg. I pulled the leg out on the 00 so that I can actually get a comparison. And when I probe that now, wait for it to start doing something. Here we go. Yeah, see, that's what that's supposed to do. And now if I take my probe and just put it down on the actual pin itself, you can see it's stuck high. Now the question is, it that chip or is it this chip holding it high? And my guess is it's probably this one. So what I can do is take my handy dandy clippers and just clip that leg and now probe that, and you see it's floating now. And if I probe the little nub that's left on this chip, you can see it's pulled high. So yeah, this 00 is dead. So we'll replace that guy and see what we get. This is a case where just flat out jumping the chip didn't work because this is shorted, internally shorted straight to 5 volts. So when you put a new chip over it, it just shorts that one straight to 5 volts as well. So, but you can pull the output pin up and you can probe your free leg on this and then just compare it to the actual pin. So yeah, I'll go ahead and replace that and we'll see what happens. Okay, I replaced that part and now you can see that bit is doing what it should. And that comes over to this guy and enables these. And this is that bit 6 and 7. So, but it's still doing this. So that did not fix this, but it definitely fixed something because that chip was definitely bad. So what did that fix? I don't know. Something in the data, because that enables this to dump data bits 6 and 7 right here. Coming out of this latch. That's a 153. RAM data. It's selecting one of 4 RAM bits and dumping those to data bits 6 and 7. Yeah, I don't know. Along with data bit 5 here. And this is 1 of 8. So this selects 1 bit of 8. I'm going to continue to scrutinize this whole little section right here. I found one dead chip. Let's see if there's something else going on. Okay, well, in scrutinizing, I found another bad part. This 153 right here. P7. That is selecting 1 of 4 RAM bits sending them to this latch, and then they're being latched out and back to this. They're being allowed to pass through to the CPU when they need to be. Anyway, this 153 up at P7 is right here. That guy's no good. Just for a sanity check, I went back to the 153s down here, and I'm giving a look-see at them, just to make sure that my analyzer is working as it should. And up here you have the enable. It's enabled low, so when this line is low, this will work according to our select line. So I have the inputs in binary, so whichever bit is selected comes down to the output. So right here you can see it's selecting the 0 bit from here to here. From right here to right here it's selecting the 0 bit. The 0 bit is 1, so you have 1 down here. Okay? And then it selects the 1 bit. Well, it's a 0, 0, 1. So it goes low right here. Stays low, I should say. Selecting 0, stays 0. Right here it selects 3. You can see 3 here. Well, it's 0, 1, 2, 3 is 1 here, so it goes high. And then it selects 2. The 2 bit is a 0, so it goes low. That's how that works. Maybe we look at this one. Selecting the 3 bit, 0, 1, 2, 3, it's a 1. And then it selects 2 bit, 0, 1, 2, it's 0 this whole time. Then we get a little blip here. So let's see, I gotta expand it right here. So let's see what this selection is. It's 0. And you can see it's the 0 bit is a 1, so it goes to a 1 really quick. And then it selects 1 and goes 0. It's just, that's a delay because I've got it at 20 nanoseconds. That's a really quick blip. So then it's 1. 0, 1 is 0. The 0 bit is a 1, so it goes high that whole time where it's selecting that 1. Then we got the 3 bit here, and it's a 0, so it goes 0. That's how that works. So that one works. So if I take this and put it up here on this 153 right here, just kind of seat it very well. And we'll go ahead and okay. Right here you can see it's enabled the whole time. It's selecting 0. The 0 bit is a 0. But we've got a pulse here. The inputs are 0 this whole time. So this should be 0 this whole time. No matter what's going on up here. This should be 0 all the time. And it's not. So when it's selecting the 2 bit, the 2 bit is a 0 as well, and it should stay 0. Same thing here. It's selecting 3 the whole time. Well, 3 is a 0 the whole time. And it doesn't really matter because it's 0. The inputs are 0 this whole time, so no matter what it selects, it's going to be 0. But we've got pulses here. And if I go ahead and check the other side, because remember this is a dual mux. Enable A, select A. This one's even worse. It's enabled the whole time. It's selecting 1. This should be 0 the whole time down here because the inputs are always 0. So the output should always be 0. Same here. It's always 0 here. So this should just be 0 the whole time. Unless this was disabled, and it's not disabled ever. Same thing, it's selecting 2, and once again, it's always 0, so this should just be 0 the whole time. Okay, now we're selecting 3, should be 0. Selecting 1 should be 0. We're selecting 2, 0, 1, 2. Okay, it goes high. I'll buy that. And then it does go 0. So when it selects 2, it seems to work. Well, not here. 3, no. Yeah, see, it's doesn't work. So that mux does not work. So I will replace that mux right there, and we'll see. That's going to manipulate that data bit. Those very data bits that I was looking at, that I was talking about, that's in that same circuit. So that's, once again, it's going to manipulate the data that is coming back to the CPU. Alright, I replaced the 153, and we're getting the same nonsense. No change on anything. And I put the analyzer back on, and we're getting the same garbage. So I'm wondering if it's the chip that's connected to the outputs, which is this 75 at E7. I think I'm just going to cut that E5 out, or that 75 at E7. E7, where's it at? Let me find that chip, and I'm going to just cut it right out of the board. Yeah, I cut that 75 out. It was right here at R7. And, of course, it's doing this. And then I rechecked this guy, and I had that one in here, the 153, and it looked exactly the same. So I put an actual 74 153 in the board, and it tests the way it should. Now you'll see the outputs. Remember how the input or the output had the pulsing, but it was 0 all the time up here? Now it's showing different values up here. Which I don't know. I just think that the 153 gives a more clear. It uses more power, of course. This is low power, but this gives a better reading. I'm going to leave that 153 in the board. Of course, I have to replace the 75 now, but I don't think that's going to make a difference. I'm just going to have to keep plugging along. There's just bad parts on this board. All right, I've come to something. This is that 125. That's this guy, remember? Where we fixed the signal that was going to the enable to these. And now I'm actually looking at those gates themselves. I'm on pin 12 out to 11, that's data 6. And we'll look at data 7 next. But this is data bit 6. And I've got a snapshot here. You can see where it is enabled. It's enabled low. And data is low. So this, when this whole time that this is enabled, this should mimic this. So it should be high, going low, and then back to high. And then I don't care about what's over here. I only care about what it does when it's enabled. When that is enabled, it must match. You see it's enabled, it's floating-ish. Garbage. This does not work. It's another bad chip. That's enabled, that should match that. That one is no good. So let's just move on down to the next gate. This is data bit 7 on that. Let's see what data bit 7's telling us. Okay. Alright, so we have it all hooked up. Now we have our enable and it's high. That's kind of high. and it's not going low. See, this chip just doesn't, flat out does not work. When this is low, this top line's low, this should mimic that right there. For that little bit of space, that should mimic it, and it doesn't. So this is not influencing the, it's not influencing the data bit, the data bus back to the CPU at all. The CPU is asking this thing right here something to do with that color bit, and it's not getting the information that it's looking for. Therefore, it's just doing this. That's my theory anyway. So we will go ahead and, because like I said, I was saying before, the CPU is asking for data. What is going on the screen right now? You know, what's the video RAM telling us? So the video RAM spits this out here. It muxes 2 bits here. Those 2 bits are latched and driven out and actually enabled and sampled through these 2 gates. And then the CPU would get that information, and that would tell it what to do next, you know. So just erroneous data, video data. So anyway, let's go ahead and replace this 125, and we'll see what we get. All right, replaced the 125, and let's try it out. There you go. All right. Much better. So bit 6 and bit 7 out of that circuitry must be trackball position blanking the color on it after it. I don't know. But yeah, that fixes that. So that's all she wrote. Now I just got to test the trackball. All the sounds. With sounds, I'm sure it'll be good because remember it had to have a new Pokey. The Pokey was bad. Color RAM was bad. Handful of logic chips. Sockets so far. Some caps and a couple others broke off. I got to replace a couple more. Crystal was missing. Yeah, so let's go ahead. I'll hook the trackball up. We'll throw this thing into test. And test it out. Okay, you got the trackball hooked up. So let's put it into test. Orient the trackball the right way. Up, left, right. Yeah, trackball works. You know, I was able to set the dip switches to, I believe, the standard. There you go. Now, test our buttons. These are the fire buttons. Good. 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 Our color RAM is goofy. Not goofy, it's just was stuck in that color. I want to hook up this. Yeah, I didn't mean it's goofy like it's bad. It's just whenever you hit a button, it changes the color. So let's check these outputs. Coin. Good. Coin. Good. Start to. Good. Slam. Good. Test. We're in test. Coin center. Good. Start. We're good. That's a complete good test. Missile command. Done. Alright, well, I'll go ahead and hook up the, get the tripod out and hook up this thing up on the tripod, and we'll play a game. Try to play a game as good as I can anyway. And check it out. Alright, let's give it a shot. Let's put a credit in. Coin left. There we go. Now we'll start. Can't do this. Can't do this with these wires like this. Uh-oh. Successful playtest. Missile command. Alright, so, okay, what was the damage on this one? 2 RAMs, sockets, TTL, it looks like we have 1, 2, 3, 4, 5, 6, 7. 7 TTL, Pokey. I washed this board really good. Crystal. And I fixed the edge. The edge connector needed to be repaired. And I did repair the edge. I believe that's it. ROMs were all good. Just needed new sockets. Yeah, so that's going to do it for this one. We'll let it sit and cook for a while and run, and I'll just go ahead and throw a couple more caps in here where needed, and don't need to bore you with that. And yeah, oh yeah, and RAM. This RAM I had to replace. This is not TTL. This is a RAM. So I had to replace the 7489 color RAM. That's all you need to do to fix your missile command. Alright. Well, thanks for watching, guys. I hope you'll all learn something, and we'll see you all on the next classic Arcade Repair. Bye for now.